Okay, let's get started. Good morning. Uh, do we have any doubts from the previous lecture? No? So one small announcement, you can collect your surprise test answer sheets at the end of the lecture. Uh, so in the last class, we were talking about CPU scheduling policies. We'll continue with that. So we started with these 5 workload assumptions that each job runs for the same time. We said that if we remove this assumption, what happens? All jobs arrive at the same time. We remove this assumption. Once started, each job comes to completion. We looked at preemption. All jobs use only the CPU, but we know that many jobs use both input-output CPU network, etc. So what happens? So we remove this assumption. So let's say we had 2 processes A and B, and now we're trying to incorporate input-output. So CPU is accessed by process A for first 10 seconds, and then process A requires disk. Again requires CPU, again disk, again CPU, and then process B is run. So we just look at the run times, the CPU run times. The CPU runtime of A is, how many seconds does it use? How many time slots? 30 units, whereas compared to B, which requires 40 units. So let's say both of them, A and B, came at the same time, and we're using shortest job first. So, and shortest job based on the number of CPU cycles. So A will run before B. But we have this issue that we have these voids in between. Can we do something about it? So if we calculate the CPU utilization, that is the amount of time CPU was being used divided by the total time taken by the jobs. So we have this process A takes 30 units, process B takes 40 units, so the total time taken was 30 plus 40 plus 20. So total time is 90. CPU utilization is 70 by 90, which is approximately 80%. So ideally, we'll want the CPU to be used 100%. The response time is for A, it's 0. For B, it first kicks into action at time t equal to 50. So response time is 0 plus 50 by 2, which is average response time is 45. Average turnaround time. So A completes at 50, B completes at 90. So the turnaround time is 70. Let's say if we wanted to incorporate IU and make this CPU utilization better, what could we do? So we could put B in between the gaps of at the time when A is using the disk. It would look something like the following. So now B only needs to execute for 30 more time units after time t equal to 50. So what's the CPU utilization in this case? 100, because we are now using 70 cycles, and in all of them CPU is being used. The CPU utilization is 100. What's the response time? So response time for A is 0, response time for B is 10. So 0 plus 10 divided by 2, which is 5. Turnaround time. So we see that now B completes 20 time units before it was in comparison to the previous method. So it takes now 70 units in total. A is taking the same time, which is 50 units. So the average turnaround time is now 60 units. We'll do a quick round of practice on our notebooks just so that we're more familiar with it. Again, this is not graded. This is just for your practice. So we're going to do 3 questions, and these are all from the textbook. So you could look at them at the time. So let's say we have 3 jobs, length, time t100, length of job 2 is 200 and 300. Can you calculate the response time and turnaround time in LCF and FIFO? So for FIFO, assume that they come in the order 10, 200, and 300. Is everyone clear with the question? Has everyone solved this? Anyone who's not yet solved this? So we want to find out the response time and turnaround time. Let's say we are doing it for shortest job first. So the first job which will be executed is the shortest one, which is P1 of 100 units, followed by P2 of 200 units, followed by P3 of 300 units. The response time of P1 is 0 because it arrived at time 0 and it's executed at time 0. P2 also arrived at time t0, but it's first executed at time 100. So the response time is 100 minus 0 equal to 100. And P3 came in at time 0, but it's first executed at time 300. So response time for P3 is 300. The average response time is 400 by 3. In terms of the turnaround time for P1 is, for P2 is 300 and for P3 is 600. The average turnaround time is 600 plus 300 plus 100 divided by 3. So 1000 divided by 3, 333.33. What if we are using FIFO instead of SJF? It's the same because we assume that P1 is executed before P2 is executed, or they came in this order. Okay, the next question, third question. Now you're using round robin scheduler with a time slice of 1. Calculate the response time and the average turnaround time. Does everyone remember the round robin algorithm? Okay, can quickly someone summarize me what round robin algorithm would do? Anyone? Yeah.
You could divide the processes into parts and then run consecutively, run them consecutively with time slice of 1.
Okay, fair enough. Yeah, that's how it will work. And it's called round robin because it works in a round fashion. So circularly you get to the same process again. Has everyone done it? Completed? Okay, who need more time? Okay, let's look at the execution trace. X-axis is showing time. So we have a time slice of 1, which means that the smallest unit of execution on the CPU is of time unit 1. So round robin for time t equal to 1 will execute P1. This is 1, this is 2, this is 3, P1, P2, P3, 3. This will again repeat P1, P2, P3, 4, 5, 6, P1, P2, P3. So we can see that it takes a block of 3 seconds to complete P1, P2, P3 one go. So an easy way to solve this could be, instead of enumerating the entire answer, let's look at blocks of 3 before one of the processes completes. So what's the first process to complete here? P1, because it's of shortest sense, which is 100. So we can see that in a time step, in a block of 3 units, P1 executes for 1 unit. So if P1 is to execute for 100 units, how many total time steps do we need? 300, right? So we go in this fashion up to, let's say, times 300.
Sir?
Yeah.
Wouldn't it be 298?
298. Yeah, that's 298. But I'm saying about the total block completion. Yeah, that's to be precise, it should be 298. P1 completes here. This is 98 and this is 299. So at time equal to 300, we have had, let's say we maintain this buffer, this data structure. And in this, we capture the amount of time left for each of the processes. At time equal to 0, we had 100, 200 and 300 units left. At time equal to 300, P1 is completed, P2 has 100 units, P3 has 200 units. So at this point of time, since P1 is completed, now we'll have the round robin working only between P2 and P3. Is that clear to everyone? So now we have units of block size 2. We have P2, P3, this is 302, P2, P3, 304. And till what time will this execute? So this will execute till the time P2 is completed, because P2 is a smaller process. So for every time, for each 2 seconds, P2 is executed for 1 second. So if we want P2 to execute for 100 seconds, we want additional time of 200 seconds, right? So time equal to 500. This is 0, this becomes 0, this becomes 100. And from point 500 onwards, let me write 500. We only have process P3. So what we'll have P3, 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 and all the cycles P3 will be running. So we require 100 more cycles, 600. So if we look at the time steps, P1 completed at time 300, P2 completed at 500, P3 at 600. So the response, the average turnaround time is 300 plus 500 plus 600 divided by 3. What about the average response time? So when is P1 executed for the first time? 0, it came in at 0. So response time for P1 is 0. Response time for P2 is, okay, someone from that side. What's the response time for P2? 1. That's the quantum period also. Response time for P3 is 2 into 1, so it's twice the quantum period. So the response time in this case is 0 plus 1 plus 2 divided by 3, which is 3. Which is 1. So if you remember the turnaround time from the previous example, it was 100 plus 300 plus 700, right? In the previous case, plus 300 plus 600. So which is 400,000 by 3. This is for FIFO or SJF. And for round robin, it is 1400 divided by 3. So we can very clearly see that SJF is far better at optimizing for the turnaround time compared to round robin. That's the vice versa when we're looking at the other metric of response time. Let's do question number 5 now. So what type of workloads and quantum length would SJF deliver the same response times as round robin? So does everyone get the question? We have to find out a type of workload and a quantum length for which SJF will be similar in response time compared to round robin. So one of the ways to approach this problem is to take the most trivial example, which is when all the jobs have same length. What happens in that case? Work it out for in your notebooks. If all the jobs have equal length, what time quantum should you use so that SJF gives you the same time response as round robin? Yeah, all the jobs are of equal length. Now think of some non-trivial example.
So the quantum length is really equal to length of second time.
Yeah, that's right. We'll have to wait for it. Let everyone solve. So in general, for all these kinds of questions, it's advisable to pick up really simple examples first, see when they work and when they don't work, and then increasingly pick up more complex examples. Similar to the way you'll solve some algorithmic questions.
So if the quantum length is longer than the period of a job, so will the CPU stay idle for the remaining part? Or
It looks at if there is any other job. So it just pushes that to the running state. Has everyone solved this? So tell me for a non-trivial case. So I'll very quickly solve for the trivial case. Let's say we have jobs of length 10, 10, 10, and they all arrive at the same time t equal to 0. So for SJF, we'll have P1, P2, P3, 10, 20, 30. The response time for P1 is 0, for P2 is 10, and for P3 is 20. The average response time is 10. Now we want a round robin scheduling algorithm for which we get the same response time. So let's look at some extreme cases. Let's look at round robin with the same set of jobs with quantum length equal to 1. If quantum length is 1, as we saw in the previous case, so we'll have P1, P2, P3, 1, 2, 3. So in this case, the response time for P1 is 0, for P1 is 1, for P3 is 2. The average response time is 1, which is way smaller than the average response time for SJF. What if we make Q equal to 2? In that case, P1 starts at 0, executes. Response time for P1 is 0, for P2 is 2, which is the same as the quantum, and for P3 is twice the quantum. So we basically want Q plus 2Q to be equal to 10 divided by 3, sorry, equal to 10. You see this equation? So we see that the average response time in round robin for quantum length of Q in this simple scenario, for the first job it's going to be 0, for the second job P2 is going to be quantum length, for the third job it is going to be twice the quantum length. So the total response time is going to be Q plus 2Q divided by 3, and that is equal. That has to be equal to the response time from SJF algorithm. So we basically want Q equal to 10. So do you see this? That if the quantum length is equal to the length of the job, when all of them jobs are equal, the response time of them is equal. Sounds intuitive also? Let's take some non-trivial example. we have jobs of length 10, 20, and 30. So what's the response time for SJF? P1 executes at time 0, response time is 0, P2 executes at time 10, response time is 10, P3 executes at time 30, response time is 30. Total average response time is 40 by 3. Now choose some quantum so that you'll execute this exact same trace. So you'll execute P1 for 10 seconds, you'll execute P2 for 20 seconds, and you'll execute P3 for 30 seconds. What quantum can we use? So again, if you have absolutely no clue about this or you're not able to figure out the intuition, pick up some trivial examples. Pick up really small q. If you pick up q equal to 1, we'll clearly not have this kind of a diagram. So we'll have P1, P2, P3, and time-wise 1, 2, and 3. So clearly we are not executing the same trace if we pick up q equal to 1. Let's pick up q equal to 10, which is the quantum corresponding to the first process. So we'll have P1 run for 10 seconds, P2 run for 10 seconds or 10 units, but then P3 will again kick in because 10 units have elapsed and P3 would kick into action. So here P2 has executed only for 10 seconds, here P2 has to execute for 20 seconds. So what we probably need is even a bigger quantum. Will 15 work? No, right? Because if we choose 15, P2 will run for 15 units and then P3 will run. We want P2 to run for its full duration of 20 units, which can be done only if the quantum is 20 or more. If it's 20, P1 executes for 10, P2 executes for 20, and then P3, because it's the alone process, will execute for its entire duration. If it's greater than 30, the same thing happens. The quiz is on next Tuesday. I hope you remember that and expect such kinds of questions. Okay, so let's go back to the assumptions again. So one of the biggest assumptions we took at this point of time was that in all of these examples we were looking at, we said that we already know the runtime of the job, but that's not very practical. So when we execute process, let's say if I want to,
So if we take the quantum length of 20 and the job is 10,
right?
the CPU will be unavailable for 20 seconds, or will the next job start at 10 seconds?
So the next job will start because you want to maximize the CPU utilization. Like what you're saying is it could be possible that there is some policy which keeps the CPU idle, but in more practical sense you'll always kick in the next job. So is that clear to everyone? Did everyone get the question?
So the answer that we came up with, that will only work when you have 3 jobs, right?
If you have 4 jobs, then what happens?
You have to take greater than 3.
So if you want to generalize, if you have n jobs, we have to have the quantum length of greater than n minus 1th job, right? Okay, so if we look at the workload assumptions, let's cancel out the last one, which is the runtime of each job is known. So this is an algorithm or a scheduling policy introduced by Fernando Jose Corbato, who won the Turing Award for this. So does everyone know what the Turing Award is? It's like the Nobel Prize of computer science. So this approach is called multi-level feedback queue, or MLFQ for short. So we saw that even in the assignment, we saw that we always want to optimize both the turnaround time and the response time, but they can very often be conflicting in nature. So if we want to optimize the turnaround time, we want to run shorter jobs first, which is like SC, like shortest time to completion algorithm, or the shortest job first kind of an algorithm. But the problem here is that we don't know the length of a job a priori. So we cannot optimize until and unless we know the length of the job. The second is we want to optimize the response time. So we worked out an example that round robin improves the response time a great deal, but it comes at the expense of a poor turnaround time. So how can we meet both these objectives, especially given the fact that we don't know the length of the job? So we'll take a quick look at how MLFQ will work. We'll look at some of the rules. So as the name itself suggests, MLFQ queues, multi-level feedback queues. So there are multiple levels of queues. So each of these queues has a different priority. So in this case, we have 8 queues in which processes can be executing, and Q8 has the highest priority. So the first rule which we have in this proposal is that, let's say we have a process A in a higher priority queue, let's say it's in Q8, versus a process which is lower in priority. Let's say it's in Q4. So A will be executing before C because it's higher priority. But what about the scenario, let's say in Q8? So we have both A and B. Which of them will execute? What do you think? Will A execute or will B execute? Yeah. So when both the processes have the same priority, you execute them in round robin fashion. You execute the first process for a quantum length, you execute another one, the second one, and so on and so forth. So these are the first 2 rules of MLFQ. The first one again, if priority of A greater than priority of C, that is, if a process is in a higher priority queue, it will execute before the process in the lower priority queue. And if you have 2 processes in the same priority queue, they will run in round robin fashion. So let's look at the intuition behind this methodology or this scheduling policy. Let's say we have a process A which is highly interactive. By interactive, I mean it's like it regularly wants to access the disk, or it regularly is looking for, let's say, keyboard input or user input. So it relinquishes the CPU very often. We want to keep its priority high, because if it's not high, the response time will suffer. So we want A to be executing very often on the CPU. So if A is interactive, we keep it priority high. Because it's interactive, it doesn't use the CPU for the entire duration. So this is something we need to keep in mind. Let's say we have a process B, which is very CPU intensive, does not require any disk access or any interactivity as such. So we can probably keep B's priority low, or we could over time reduce the priority of B. So the intuition behind reducing the priority of B over time is that we want processes such as A to be always running on the CPU. Processes such as B, they can be kicked out because they're not as such very interactive in nature. So we'll come up with the first attempt of solving MLFQ. Let's say we have a process A which requires to run for 200 units or seconds. And we have 3 queues, Q2, Q1, and Q0. And the time quantum is 10 seconds. So by time quantum, I mean that the time quantum of round robin, or the time quantum of execution in each of these queues. So what's going to happen is that Q2 has a time quantum of 10. For 10 units, process A runs on Q2. It gets so before that, so whenever a new process comes, it's placed in the highest priority queue. Why would you want to do that? You want to minimize the response time, and you want to give every new job a shot at the CPU. So each new job comes in at the top of the queue. It executes for the time quantum, which is in this case 10 units. Since it's used up the entire time slice of 10 units, it goes to a lower queue now, low priority queue now. It executes for another 10 seconds. It again uses up the entire time quantum of 10 units. goes to the lowest priority queue where it keeps on executing. So this gives us the next set of rules for MLFQ. Rule 3, that any new job is placed at the highest priority level. And rule 4a, that whenever a process has used a time slice without giving control, it's demoted to a lower queue. So we look at this notion of without giving control. Why is this mentioned there? Okay, so let's look at the case where a process is both CPU and input-output bound. So let's say this process runs on Q2 for some time, which is equal to the time quantum of Q2. It gets demoted, but then before it is going to give up the CPU, it accesses the disk. So it means that this process is highly interactive in nature. So what this rule would suggest is, for such interactive processes, we don't reduce the priority. We keep the process at the same priority. Okay, so let's look at how MLFQ is going to approximate shortest job first. Let's say we have a process which we don't know its length yet. We only know that it's placed at the highest priority Q2 at the start of time t equal to 0. Runs for the time quantum t equal to 10. It's demoted at time t equal to 10 to the lower queue. Runs there for another 10 seconds, 10 units. It runs for another 80 units on the lowest queue. But then we have another job B which arrives, which is shown in the lower gray. It now executes on Q2. Because it's a new process, it starts with the highest priority queue, which is Q2. It gets demoted after completion of 10 units, and it runs on Q1, and it completes at this time. It's a short job. And then again, Q0 is going to, so Q0 is again going to have that big process, that CPU intensive process. So can anyone explain how MLFQ approximates SJF in this example, trivial example? So
the shortage of
yeah, so the shortest job, let's say it came in at, so we assume that this process, all of these processes are preemptive in nature. So the shortest job came in at time t equal to 100. We gave it a full shot of running. So by meaning that, if you put it in the highest queue, it's very likely that it can get executed completely. If it was a long job, it will anyway go down the lower queues. If it's a short job, it will get completed in the higher priority queues. So the short job came, it got the highest priority, it got executed, completed, and after that, the long processes again continued. So again, but you can question that, if we had chosen a lower quantum and things like that. So these are some design decisions and some questions that we'll look at later.
What if a process takes like a large amount of CPU time initially, but then it is after some time it is more of interactive process?
That's precisely one of the shortcomings of this MLFQ attempt 1. I've mentioned that as one of the limitations. We'll come to that in 2 minutes. That's excellent point, excellent observation that this is one of the shortcomings of this approach. That if a process changes its nature over time, in this case it will just continue to remain on the lowest queue. So we need some mechanism of increasing the priority again. Okay, so let's look at the case where we have input-output plus some CPU-intensive job. So we have a process shown in black, which is very CPU-intensive, runs for 10 seconds, 10 units on Q2, demoted to Q1, runs again for 10 units, again demoted to Q0, keeps on running. But then there is a process shown in gray, which is very input-output intensive. So it runs on the CPU for this very thin duration, gives up the CPU, accesses the disk. So during that time, so it's put on the highest priority queue. But since it's accessing the disk very often, it's not using its entire time quantum. We keep it in the same priority state. So essentially, this job shown in gray remains at the highest priority for the entire duration. Now, is this problematic? Okay, so let's think of as a hacker would do. Let's say you want to act as an adversary. You want to compromise some system, or you want to have access to the system most of the time. What would you do?
Make the program interactive.
So one of the ways is to make the program interactive. And if I'm very miser, or if I'm very good at gaming the system, I would look at this scheduler gaming. So let's say the time slice is X units. I'll run the CPU for, let's say, 99% of the time quantum, and then make a system call, or make a disk call. I may or may not require the disk. I could just write to a temp location, just unnecessarily trying to remain at the same high priority. Again, request an input output remain in the same priority, and then again I'll go back to step 2. So in this way, I'm effectively remaining at the same priority. I'm the only process which keeps on executing, and because of this, I'll also have starvation. So some of the jobs which are very CPU intensive, they'll keep on waiting in the last lower queues. They'll never get a chance to execute. So we need to do something about it. The third shortcoming is, as he was suggesting, that if there is a change in behavior, let's say if I had a process which was initially very CPU intensive, I had to do a lot of calculations. But after I've done the calculations, it's a very interactive process. Every 2 milliseconds, I write to the disk. So it's very bad for such processes that they've already been demoted to the lowest queue. We cannot do anything about it. So we need some solutions to all of these problems. So effectively, if we look at some of these problems, we observe that there is only a single way in which the priority is flowing. That's from the highest to the lowest. Can we actually change something to solve any of these problems? Any thoughts?
On disk access, it can go.
On disk access, it remains at the same level. So if you move it even further up, that's actually a problem. Because I could again game the system. Refresh at?
After some time.
Okay. Any more thoughts? So this is clear that we want to increase the priority of some of these processes. How we do that is the question. So we have one suggestion that we could refresh after every few, after some time quantum. Is there any other strategy we could follow?
Can we consider it as two processes?
Can we?
Consider it as two processes.
How will that work?
At the point where it's it's changing into interactive process, so can we break up in?
Right. So the suggestion is that if the process changes to an interactive process, we then increase the priority. So it's a good suggestion that if at some point of time in the timeline we see that a process is, let's say maybe we maintain a count in the out of the last number of cycles, how many of them were used for input output. If that exceeds a certain threshold, you increase the priority. But the more intuitive or the easier way is, as he suggested, that after every few time slices, we increase the priority of all the processes. So what that will do is that ensure that there is no processes which is starving, and because an old process which was maybe CPU intensive earlier, it gets another chance to go to the top of the queue, and maybe if it's now an input output process, so it will remain at the top of the queue. So we call this priority boost. Let's look on the left hand side. We have 3 processes, so Q2, Q, and on 3 queues, Q2, Q1, and Q0. For priority boost, what we want to do is every few time intervals, all the processes move to Q2, to the highest queue. In this case, the only process which is at lower priority is this black one. So only this will be moved to the top queue, because the other ones are anyway at the top queue. So in this case, what's happening is every 50 time units, the black process moves to the top of the queue. Again runs for 10 units at Q2, again runs for 10 units at Q1, again demoted to Q0, again, time equal to 100, it moves to the top of the queue, runs, completes after a certain time. So this is the fifth rule, that after some time period S, move all of the jobs in the system in the topmost queue. This prevents process starvation, and it also handles if there is a change in behavior. Okay, so are you going to ask why does this not go down? I think what's happening is it's probably moving down the queue, but this is only showing the execution. So when the process is actually being executed on the CPU. So at all these points in time, there is something running on the CPU. So you cannot, as such, execute this black process on Q1. I think it's just a matter of convention, but effectively it's moving down the queue. That's what happened. That is what is happening. Now, one rationale of it not moving down the queue could be, let's say if this ran only for a very short duration. If it ran for lesser than the quantum length, let's say the quantum length is 10, it ran only for 5 units, and some other processes came in the queue. So it still has some 5 time units to run on the same queue level. Okay, so there are a few questions when we look at this time period S, at which we refresh the priority, or we put all the processes at the top of the queue.
Sir, what is the preference for program on the same?
The preference for the program on the same queue, so in the set of examples which the book has taken, it's by the process ID. So J0 executes before J1 executes before J2. But this is largely a matter of convention and a matter of, in an actual CPU system, you could effectively randomize them. Or you could just use some kind of a convention. So if we choose a very high S, what happens? Let's go back. In this example, if S was very high, what happens? It means that after a very long duration, the priorities are increased. So effectively, that is effectively in some sense starving the, if we take S tends to infinity. So it's almost as if no priority boost happened. What if S is very small? Sorry, any answers? S is very small. So if it's S,
We are not giving advantage to the process which is more interactive.
Yeah, that's again an excellent answer. So if S is very small, we'll keep on putting the CPU intensive jobs on the top of the queue. If we keep on doing that, it's not giving a fair share of the CPU to interactive processes. So we'd always want the interactive processes to have the first go at the CPU. Okay, so we have solved 2 of the problems. We have solved the starvation problem. We have solved the behavior change problem, both of them by having the priority changed after every S seconds, so priority boost. But we've still not solved the scheduler gaming problem. So one of the reasons why this was a problem was because of the rules 4A and 4B, which could be gamed. So we said that 4A said that demote processes, if it executes its own quota, and process 4B said that process gives up the CPU before time slice, then it remains in the same priority. So 4B is the one which we really need to make some changes to. We replace both of these processes with, both of these rules with a single rule. It says that once a job uses a time allotment at a given level, and regardless of the time that how many times it has relinquished the CPU, the priority is reduced. So did you get this rule? Do you get how this is effectively allowing us to not game the system now? So we can look at an example to make it more clear. So on the left hand side, we're looking at if rules 4A and 4B, the older rules, were in place. The gray job is run by a person who's very smart who wants to game the system. Out of the total quantum of 10 units, let's say, it runs for 9 units and then it accesses the input output. But still, since it's not taken up the entire time quantum, the process gray remains in the same priority level. Let's look at the new rule 4. So it executes for 9 time slices. In the next run, it wants to execute again for 9 cycles, but it executes only for 1 cycle. Because now 9 plus 1, can you see the very thin bar on the right? So it now executes for 9 plus 1, so the total is executed for 10 time cycles, and now it has to be demoted to a lower key. So this is one way which leads to better accountability, and it leads to the reduction in, so it reduces the possibilities of gaming the system. So there are these 5 rules in summary, which we should again have a look at before we solve again some practice questions. So we have the first rule that if priority of A is greater than B, that is A is on a higher queue compared to B, then A will run, B doesn't run. If A and B are in the same queue, they have the same priority, then A and B will run in round robin. And as a matter of convention, we'll look at, in round robin, we'll run the process with the lower process ID first. Rule 3 is that if a job, whenever it enters into the system, it plays at the highest level of the queue, which is especially useful for interactive processes, and it also enables the processes, the algorithm to look like which algorithm? SJF. Rule 4 is, which was just made to prevent gamification. So it says that once a job has used up its time allotment at a given level, irrespective of the number of times it has relinquished the CPU, it's demoted to a lower priority queue. And rule 5, which was made to prevent which problem? Starvation and behavioral change. So this says that after every time period S, move all the jobs in the system to the topmost queue. Okay, we'll now practice a couple of questions at least to see how this entire process will move. You can run the simulator at your own time at home. So we'll start with 3 jobs. We have 3 queues, Q2, Q1 and Q0. The quantum length of all of the queues is 10. There is no boosting, which means that we don't increase the priority ever. And the run times of these jobs are 19, 24 and 22. So do you get the question? We have 3 jobs, start at time 0. Their execution times are 19, 24 and 22. And the quantum of each of the queues is 10, time t equal to 10. 3 queues, 3 jobs. Find the response time and the turnaround time. You don't need to worry about I/O. So these are pure CPU processes. So the way I'd suggest solving this is to draw in a similar fashion to the queues we were seeing in the previous examples. Draw 3 queues, put the processes, draw the entire timeline, and then see what happens. One way I would solve this problem is to maintain this kind of a data structure where for each time t, I maintain the amount of running time which is left for the three processes, three jobs, J0, J1, J2. I draw the three queues, Q2, Q1 and Q0. Each of them have quantum length of 10. So at time t0, just because of the fact that we said that process J0 will execute before J1 will before J2, just as a matter of convention. The time quantum is 10. So at time t equal to 10, we have process J0 executing. At time t10, because it's executed for 10 units, we have 9 units left, 24 and 22. Now we'll have J1 and J2 now also continue in round robin fashion. We'll have J1 run for another 10 seconds, J2 run for another 10 seconds. At time 20 and 30, we have still 9 units left of J0, 14 units left of J1, and 12 units left of J2. Sorry, 22. 9, 14, and 12 units at this point of time. Now at time t equal to 30, in fact, even at this point of time, process J0 would have moved to a lower queue, but it's not getting the CPU. At this point of time, it gets the CPU. All of them are in the lower queue, and we can now execute them again in round robin fashion. So from 30 to 39, because it requires only 9 units for left, J0 will run. At time 39, this is 0. J1 still requires 14 units, so it will take up the entire quantum of 10 units. J2 wants to run for 12 units, but will take up the time quantum of 10 units, 59. So we have 49, 59, and eventually at 59 we'll have 4 and 2. Now J1 and J2 move to lower queues. J1 executes for 4 seconds, completes the time 63. J2 completes the time 65. The turnaround time of J2 is 65, J1 is 63, J0 is 39. So the average turnaround time is 39 plus 63 plus 65 divided by 3. And the average response time is 0 plus 10 plus 20 divided by 3, which is 10 units. Any questions in this example? Okay, we'll start the next lecture with a question which I want you to work it out at home. So it's the exact same set of job lengths. They all arrive at time t equal to 0, but the quantums are different. So quantum for Q2 is 2 units, 10 units, 15 units.